Today we want to define dot product. Now, right now we're not going to give it any physical meaning quite yet. The dot product between any two vectors from the same dimension, if I say they're both in Rn, then u and v of this form, then u dotted with v is equal to u1 v1 plus u2 v2 plus all the way to un vn. The formal notation is the sum from I equal 1 to n of ui vi. It does not matter what dimension you're in as long as the vectors are the same dimension. Now in this class we're only going to be working with vectors in R2 and R3. So if we're using that u and v are in R2, then u dotted with v is simply u1 v1 plus u2 v2. If I'm in R3, then I add the third component. Now for the next phase, I want to remind you of something called the Law of Cosines. Anytime I have a triangle and I know all three sides and I know one of the angles, then the relationship between these three is that c squared is equal to a squared plus b squared minus 2ab times the cosine of theta. If it turns out that theta is 90 degrees, then this last term goes away and I simply have the Pythagorean theorem. Now we're going to use this in a moment, but instead of having a triangle with these lengths, we're going to create a triangle using vectors. Now consider the triangle formed when I take two vectors, u and v, and then I take the difference u minus v. Now u minus v would be v in the negative direction added on to u, and I'm just going to insert it at the end here. So I have a triangle with a similar situation as before, so I know based on the law of cosines that if I consider the lengths of these, I would see that the length of u minus v is equal to the square of the length of u, the square of the length of v, minus 2 length u, length v, cos theta. Same as before. So what we want to, square. So what we want to do is put in the components that we know. Now, u minus v is simply u1 minus v1, comma, u2 minus v2. So when I square this length, I'm going to have u1 minus v1 quantity squared plus u2 minus v2 quantity squared. Here I'm going to have simply u1 squared plus v1 squared, u1 squared plus u2 squared, plus v1 squared plus v2 squared, and then minus those products here. Okay, so now we want to expand this quantity and see where that gets us. Now if we expand the left side here, we're going to get u1 squared minus 2u1 v1 plus v1 squared plus u2 squared minus 2u2 v2 plus v2 squared. Now we've already got the right side expanded, and you notice we're going to get a lot of cancellation here. Basically the squared terms are all going to cancel, and what that leaves us with at this point is if I factor out the negative 2, I'll have negative 2 times u1 v1 plus u2 v2 equals negative 2 length u, length v, cos theta. So multiplying both sides by negative a half, we would get u1 v1 plus u2 v2 equals the product on the right. But we notice this is simply the dot product. So we've got an alternate way of determining dot product. We can do it by using the components of the vectors, or if we know the magnitude and the angle, we can do it this way. So this alternate formula is the one we probably use in physics the most. So we have two ways of finding it. But the nice thing about this formula, it also allows me to calculate the angle between the two vectors by solving for theta. Namely, theta would be the inverse cosine of u dot v over length u, length v. Usually we would leave this in degree form because we're not going to use that angle for the calculations, but more for descriptive purposes. Probably the most important application to dot product is the concept of work. We know that work is force times distance. Well, it's not exactly correct. It's not force times distance unless they're going in the same direction. It's actually the dot product of the force vector and the distance vector, which is a length in a direction. And in order to perform this, we now know this is the magnitude of the force, the magnitude of the distance, and the cosine of the angle between them. And the example I like to use is, I'm pushing a refrigerator across the room and I want to know how much work I got done in pushing it across the room. Well, all I have to do is multiply the amount of force I applied times the distance I traveled. But what if I want to push it across the room and I end up going off at some angle theta? Well, then not all of my force was directed across the room, only a portion was. And so that's where this part comes in. So I'm pushing it, I want to go that way, but I end up pushing it this way. Well, then I only get that much. And therefore, that's where the cos theta. What if I want to go across the room and I push it completely sideways at a right angle? Well, then I'll find cosine of theta would be 0 and I got no work done in the opposite direction. Or worse, I want to push it across the room and I end up going backwards. Then theta would be 180 degrees and I would actually get negative work done. That concept makes sense because it now means I would have to perform positive work just to get it back to the starting point. So work is the number one application that we do throughout this course, and it is simply the result of the dot product. Now I want to introduce one of the most important applications of dot product, and that is projection. I've got a vector v and I've got a vector u. They're going in different directions, an angle of theta. And I would like, first of all, how much of u is going in the direction of v? And if so, I want to express that as a vector. So the first thing I'm going to do is come down and make a right angle here and consider that vector right there. This is the portion of u that is actually in the direction of v. And we call this piece right here the projection of u onto v. V is the subscript, v is the one I'm going at. I would now like to describe this vector exactly. Well, the first thing I can do is figure out what is the length of the projection vector. Well, there's a little SOHCAHTOA action here. I know that the cosine of theta is this length over the length, so therefore the projection would simply be the length of u times the cosine of theta. Now this is a magnitude, this is a number, this is the length of this vector, but it's not the vector itself. This vector is in the direction of v. So what I want to do is figure out the unit vector in the direction of v, and then multiply it by this magnitude, and that will give me this vector. So let's suppose the unit vector in the direction of v is maybe that much. It's a short little piece. So this vector right here would be 1 over the length of v times vector v. I want to take that unit vector, I want to multiply it by this magnitude. In doing so, I will get the projection vector. So I can say then the projection of u onto v is this times this, which would simply be length u cos theta over length v, that's a scalar, times vector v. Now, this is a very, very inconvenient form of a vector because I only gave you the vectors u and v. I didn't give you theta, so you'd have to do a lot of work to calculate the cosine of theta and then work it all back in. But what if instead I said, let's multiply the numerator and the denominator of this quantity simply by the length of v. If I multiplied numerator and denominator of that quantity by the length of v, then this would become length u, length v, cos theta in the numerator, length u, length v in the denominator, and that simply gives us u dot v, and by the way, times v, sorry. That gives us u dot v over v dot v, which is a scalar, times vector v. And I don't care what the original vectors are, this process will never be difficult because all you're doing is using the components. You're never actually calculating the angle. So this is called the projection of one vector onto another. This is a very useful form. Now, all of the results I'm showing you, I've derived in 2 dimensions to make the pictures easier to understand, but every one of these results is valid in every dimension as long as u and v start off in the same dimension. The one thing we will never do is take vectors of 2 different dimensions at the same time. There's actually no use or mathematics for that. So this wraps up our discussion now on dot product. Do look at the notes that I posted online. There are several examples, and between the notes and this video, you should be able to figure out everything you need.